Hello everyone, welcome back. I hope you guys are safe, keeping yourself, your family, your loved ones safe with COVID-19 situation what we have these days. Um, Stay at home, whatever you can do, and nonetheless don't forget to watch LeProFesSEUR lectures. Stay at home, and what else I can say. I wish you all the good health and keep watching my lectures. Uh, the VLSI interconnect is a very interesting topic. We need to know, we need to be aware of what are interconnects. They play a major role. Almost 70% of the chip area is dominated by interconnects. All right, so let's start. Let's start from the very basic concept. Okay, as you can see, we have this inverter, pMOS and MOS. So we have two devices, okay, pMOS and nMOS, and they are connected to the input voltage, output voltage, power supply, VDD, and the ground. Okay, and to connect the devices, okay, we need some mechanism. Okay, or in other words, you may call it, we connect the devices via wires, and those wires we call it interconnects. Or in other words, interconnects are nothing but wires connecting the transistors. All right. Now, in this small diagram, basic diagram, if I have to say how many wires I have, let's count it. Okay. So one wire between V in to another connecting wire, then next wire between this joint to the pMOS, and similarly we can keep counting the wires. Okay, now you may call it one long wire or segment of wires. Essentially we are kind of considering horizontal or vertical lines. Think about it, when the wires are going to be routed or laid out, they are horizontal and vertical lines. Okay, so each horizontal line and vertical line, okay, we consider them as wires. We can always, put repeaters or break the long wires into smaller ones. There are some good reasons to break the long wires into smaller wires. We will discuss it a little later. Nevertheless, so if we count here, we have 14 wires. Good. So I hope you got the basic essence of how much dominating part of the interconnects is there in chip design or integrated circuits. Good. Two devices, pMOS and MOS, and 14 wires. Alrighty. Now, if we have to draw a cross-sectional view of the layout of this small circuit, how would it look like? So I tried to conceptualize it and try to draw a sort of picture which gives an idea. If I have to make a cut of the die, or let's say where this transistor layout is, so it will look like something like that. We have N well, P well, and you have nMOS and pMOS sitting in these wells. Okay, and the connections between nMOS and pMOS, we have the poly, and we have the via connecting to the upper metal layers. Okay, here I'm showing M1 to M15. Considering we have like 15 metal layer process, can be like less, like 7-8 metal layers. Nevertheless, there may be in between metal layers not showing in this diagram, just to make it very very simplistic figure to understand. And we have the oxide in between. You may also go in detail about the basic layout in some other lecture I might have discussed, or in a textbook. Good. So we are not going to be discussing about the layout, how it is done, but our focus is to mainly discuss about the interconnects. Interconnects, what we just saw. We can classify interconnects in different categories. Let's say global interconnects, semi-global interconnects. Global interconnects means that those are used for routing the global nets, which means power nets, ground nets, clock. Well, clock can be in semi-global, but mainly to do with the VDD and VSS rails. Okay, and then the local interconnects, which connects the devices. All right. Okay. Now, you all might have understood calculus in your first year engineering or high school. So if I have a big sheet, think about this big sheet of metal, right, placed on the top of the oxide, and then in between there are holes in the oxide layer. So if I have to estimate the resistance, okay, so what we do in calculus, we chop the whole thing into smaller pieces and then do the integrate. Okay, so that helps us to mathematically formalize the model. So if I have to take a smaller piece, a smaller segment of this metal, then I can approximate and try to come up with some mathematical equations to know what is the resistance it is offering, what is the capacitance and inductance, and other various physics parameters, okay, or physics equations I can form. So I'm talking about a very small geometry, at a nanoscale level, and then I'm taking a very tiny portion. And it's easier for mathematics to go with a square, rectangular shapes. So let's take this smaller piece and let's approximate it as a rectangular three-dimensional bar. Okay, you may think of memory stick sitting on the table. Okay, so this oxide layer is, you can think of the tabletop, and your memory stick bar is sitting on the top of the table. So you can visualize that way. Good. Alrighty, so it's nothing but the zoomed out version what is shown here. If I have to say how long this bar is sitting on the tabletop or the oxide layer, let's call it the length L. Okay, how long is the rod, or let's say memory stick bar. Okay, and then width of the bar is let's call it W. And how thick is the bar? We are talking about three-dimensional geometry. Okay, so let's call it T is the thickness. Okay, now we were saying about it tabletop, right, oxide layer, so it will offer some height. What is the height of the tabletop? Okay, so let's call it H is the height of the tabletop. So we have basic we formalized the basic variables. Okay, now let's try to think in that terms. Okay, remember that L, W, T, and H, we will be using these variables in the equations. So remember that. All right. Now, so I have taken one smaller piece. What if I take one more smaller piece adjacent to it? Then how it would look like? It would look like another memory stick sitting at the tabletop. Okay, and at what distance it is sitting, or what is the gap or adjacent distance between two memory sticks or two bars? Let's call it S. Good. The ratio of the thickness of the bar to the width is known as aspect ratio. Okay, and S plus W means the sum of the gap between two adjacent bars or wires or wire segments plus the width of the wire. It's known as pitch. Okay, and that all depends, like how wide wire my process technology or can make, right? Means the TSMC or Global Foundries or Intel, wherever we have the manufacturing of the semiconductor devices. So how wide they can make it, right? So they call it something called pitch, right? So you might have heard the term of 7 nanometer, 9 nanometer, right? So we talk about in terms of pitch, means the minimum gap between two conductors or two conducting wires. So these wire segments are nothing but the conductors. Okay, good. Now another important thing to understand or to make an analogy, okay, of this memory stick or wire segment or bar which will carry the current is to have the analogy with the leaky water pipe. Think about at home or wherever it is, you have a long water pipe, okay, which has holes at the bottom. Okay, so means like it's like a coarse or some kind of water pipe you might have been bought at home hardware or where you find the stuff, gardening stuff, right? So sometimes you get that pipe where little water is leaking from the sides of the side wall of the pipe, right? So let's call it, let's formalize or approximate it. We have some holes at the water pipe, okay, water pipe walls. And you may think about some kind of a thorough, right? Thorough, which from where the water is leaking through the side walls of the pipe. And since the water is flowing, the water wheel, think about, there is a water wheel at the very end of the pipe which is getting rotated and throwing the water through the pipe, and water is coming out from the other end, but it will not be the total amount of water which is entered and getting out, because some of the water is wasted, right, through the side walls, it's a leaky water, right? So that throw capacitance that can be analogous to capacitance. Okay, so the capacitive capacitor is storing the leakage current, for example. So current will be leaked and some kind of a capacitive or capacitor will be formed. Good. And then the water pipe itself, when the water is flowing, it will offer a resistance, right, along the flow of the water. So we can make an analogous to the electrical resistance. Okay, and water wheel is rotating, means that at that end the conducting currents are current fields are meeting, is some sort of analogous to a inductance, electrical inductance. So think about in that terms, and so the electric current flow is analogous to the water flow through the leaky water pipe. So that's we can call it wires water pipe analogy. That helps to visualize how the current is going to be flowing in the interconnects. Good. Now we are seeing here, right, the water pipe or water pipe, leaky water pipe is analogous to interconnect. Okay, that offers some resistance and throw capacitance, so R and C, resistance and capacitance. Okay, so resistance, capacitance, and inductance, these are three pillars of electronics. No matter what you do, no matter what device what hardware, what chip you're working with. Okay. At the physical level, these are the three pillars: resistance, capacitance, and inductance. Three pillars of whole electronic industry. Like algorithm is one pillar of whole computing industry. Same way, resistance, capacitance, inductance for whole electronic industry. Alrighty, so that a small representation of this circuit resistance capacitance can be analogous to if we have multiple wire segment or pipes, can be shown or approximated with this model, where n is nothing but the number of segments in the wire or number of wires if you have small wires. Alrighty, we have different approximated models scientists have came up with. One of them you might have found in textbooks, or all of the models are actually discussed in textbooks. L model, lumped model, RC delay lumped model. Then second one is where you see the difference. In the first one is a very simple resistance and capacitance. Capacitance at the one end of the resistance. Then the T model, where you have capacitor in the middle and the resistance is half on each side of the capacitor. And then one more kind of model where you have half capacitance on each side of the resistance, which is called pi model. Out of these three models for approximating the circuit behavior, pi model seemed to give better results between the approximated model results and the real circuit delays. So pi model seemed to give better results. This is widely used as well, and variant of that model are being used in modern simulators, which help us to estimate the various parameters and the delay associated with the circuit. All right, pi model, good. Now let's talk about the resistance. Okay, so we have this wire segment or this interconnect. So if I have to approximate the resistance of this interconnect, okay, so that interconnect wire segment will offer a resistance. How can I express it? So resistance is given by this equation, rho divided by thickness of the wire multiplied by length divided by width, length divided by width of the wire. Rho is nothing but the resistivity, and rho divided by T or thickness is known as sheet resistance. Good. Now let's talk about the capacitance. We have talked about the resistance. Now let's talk about the capacitance. Now we have capacitance between the line to substrate, or since we have this dielectric substrate, right, or dielectric oxide, so it's called the term is called line to substrate capacitance, and it is approximated with this formula: Cox equal to Kox epsilon WL divided by H. H is nothing but the height of this oxide, or in other words, when we were making an analogy with the tabletop, so height of the tabletop. Kox is nothing but dielectric constant and epsilon is permittivity. So this equation and variant of that equation, depending upon how accurate we want to have the prediction, are used. But that at the very basic level, this is the capacitance line to substrate capacitance we have to consider. Now we have to consider for this, we have to consider for this as well. In this diagram I have only shown for one. We have one more kind of capacitance, which is the capacitance is between these two adjacent interconnects. We call it interconnect lines or capacitance between these interconnects. Since these are two very adjacent, they will offer some kind of a capacitance. You may call it a coupling capacitance as well. Different names, okay? And this is approximated with this formula, where coupling capacitance or capacitance between interconnect lines is equal to Kox. K is nothing but the dielectric constant, oxide, epsilon. T is the thickness of the wire segment or interconnect. L is the length of the interconnect, and S is the spacing between two adjacent interconnect wires. So we have two capacitance. Capacitance is quite important here then. We have the capacitance between line to substrate and the coupling capacitance. Alrighty. So this is kind of a very rough model that we have two types of capacitance, coupling capacitance and capacitance between line to substrate, or which is offered because there is the oxide layer and the resistance. So that gives a complete picture of resistance and capacitance. Typically, low K dielectrics are used at different process technologies, and copper wires are preferred or for interconnects, so that we have lower resistance, and low K dielectric we will have the lower capacitance. And if we can reduce the resistance and capacitance, we can reduce the circuit delay. Circuit delay is dependent on the resistance capacitance or proportional to it. Another important thing is inductance. Okay, so as we said already, resistance, capacitance, inductance. Resistance and capacitance are easier to extract than inductance. Inductance is difficult to extract from the layout. Nevertheless, in modern day, engineers prefer or shorten up the wire so that inductive effects can be ignored. Those are negligible. Okay. Why we do have inductance? Well, changing currents. This current is flowing through the interconnects. Okay, the current will change, and that will induce the field, and due to the field effect, right, those currents will induce a voltage, and that voltage will be proportional to the rate of change. Or in other words, voltage directly proportional to the change in the current. Okay, or nothing but if we put the constant, proportionality constant, V equal to Li di over dt. This Li, constant of proportionality, is nothing but the inductance offered. We can say that coupling between wires induces inductive crosstalk. As we saw, the two wire segments or interconnects adjacent to each other, we saw the coupling capacitance. In the same way, there is a inductance, because two wires are running very close to each other. That will induce the inductance, and we would have the inductive crosstalk. Okay, and crosstalk is very notorious thing. Is sort of it makes life more complex. Crosstalk analysis and fixing the crosstalk is one of the very important tasks at the VLSI physical design. nowadays modern tools, they help engineers to close that, but it's quite important to understand what are the reasons of crosstalk. So two important reasons for crosstalk. One is the coupling capacitance and coupling inductance. Okay. If I have to write an equation to determine the how much is the inductance, okay, I can write inductance by this formula. Now this formula is written in your textbook and in physics textbooks. There is nothing novelty here. L is nothing but our length of the wire or interconnect. Ln is the log, natural log. H is nothing but the height from the ground, substrate height, what we saw, height of the tabletop. W is the width. Okay, so we don't have to go in detail how this formula has arrived or not. We can look in the book, textbook. Okay, the important thing is to understand what this formula says and how we can calculate the inductance. Okay. Now there is an assumption for this formula is that the width is width of the wire W is very less as compared to H, and the thickness of the wire is negligible. If there is a significant thickness of the wire, that depends again on the process technology node. We might have to change our formula. That formula will not give an accurate result. Nevertheless, this is a very basic conceptual level formula. Modern design automation tools, they use sophisticated version which mostly are proprietary to calculate the inductance. More or less, there is you can't just directly feed the value into the formula. I mean, it needs to do calculations on a three-dimensional geometry. Extraction of inductance is quite complex, not straightforward. All right. Now let's talk about the impacts. What interconnects impacts are. Okay. So first impact is of the energy. Right. Long wires, they require significant energy to switch, and partly because long wires, they have a very significant amount of coupling capacitance and the line to substrate capacitance. And the capacitor is charged, so think about your charging, discharging a very huge capacitor. You need the huge energy for switching. Okay, so long wires require significant energy to switch. Second thing is that as we saw earlier, the long wires, they induce the resistance and capacitance, and in other words, that introduces the delay. Okay, so that overall that increases the circuit delay. Crosstalk delay effects due to coupling capacitance. Okay, crosstalk delay effects due to inductance and other inductive effects. All right. Temperature effects. That's very interesting. So far, we found that, okay, capacitor, no problem, we don't have a temperature, but how about the resistance? The temperature on-chip thermal estimation, okay, or temperature of the full chip, it has become a very big area recently, especially when the geometries are in nanoscale area. The temperature, the interconnects get heat up, okay. So there is a temperature effect, right? And the how the heat transfer happens, it is not analogous to the electric current flow. So electric current flows in one direction, right? Horizontal, right? Or or along the flow, like along the water, right? Horizontally current flows. But in terms of the heat, it also flows vertical or longitudinally and laterally, right? I'm sorry, my pronunciation is bad here, my apologies, but the transfer of heat is not only horizontal but also the vertical at the same time, and then the coupling effects. Okay, so coupling effects of the adjacent neighbors, how the heat is going to be transferred, right? So your devices are at the very bottom of the metal stack, and then they are producing the heat, right? They are getting heat up, and then how the heat energy is transferred, right? Again, it's complex. Calculations are a bit complex, and one needs to do Monte Carlo simulations and whatnot on three-dimensional grid, which becomes not feasible when we are dealing with billions of transistors on the chip in real time. So there are certain things which we have to accommodate and think about it, right? So modern tools, for now, we saw it, right? Modern tools, they do estimation of how much power is getting consumed by the chip, and then they try to analyze the how much chip is going to be heat up. But that's not 100% true. That's why we see the difference between theoretical predictions and the actual results. Okay, there is a lag, and the current is not analogous to the heat transfer. Okay, so electrical energy and heat energy, both are two different things. So temperature effects because of the resistance of the long wires or interconnects. So we saw that interconnects are very, very important, right? Very, very important piece. We should not neglect them. We need to understand. So I guess the objective for this lecture was to give you an overview about the interconnects, different issues associated with the interconnect. The more refined or detailed on each area, let's say RC delay model, we can discuss it in some other lecture. Nevertheless, interconnects are very important. Thank you very much. I hope you guys have enjoyed it.